Hey guys, now we're going to look at acceleration due to gravity. Recall that acceleration is the rate of change of velocity. It's how much the velocity is changing as time goes by. So speeding up, slowing down, changing direction, any of those things. And what we're going to do is we are going to look at how objects accelerate at the Earth's surface. So I found this lovely simulation on the internet, and when you hit play, it shows what would happen if you dropped an object on Earth. And what you see here is that blue dot is the object that's falling, and as it falls, it picks up speed because of the Earth's gravity and falls faster and faster and faster, and that's what we're going to talk about. So first, I want to give you just a little bit of information about gravity and what that is. Gravity is an attractive force that occurs between all objects with mass. So as weird as that sounds, you do have your own gravitational force. It does happen to be very, very small. So everything around you, look around, everything that has mass has its own gravitational pull. It pulls everything else with mass towards it. But unless you get something about the size of a planet, the force is so small that you don't even notice it. So on Earth, really the only gravitational force that we notice is the force from the Earth itself, because the Earth, compared to us, is extremely massive. So what happens is this force of gravity will cause everything to accelerate towards the center of the Earth, so down for us at the surface. And everything always accelerates with this characteristic acceleration. Now, the actual value is 9.8 meters per second squared. However, while we're getting the hang of this, there's nothing wrong with using a gravitational acceleration of 10 meters per second squared. It's pretty close, and it is much easier to work with as far as the math goes to get you an understanding of what's going on. And so what that means is that every single object accelerates towards the Earth at 10 meters per second squared, regardless of weight, size, whatever. Now, air resistance can slow it down. Think about a feather falling. A feather doesn't fall at that same acceleration as everything else because the air actually pushes up from underneath it. But if we ignore air resistance, everything falls with that same acceleration. And this is why it doesn't matter how heavy an object is. Heavy objects fall at the same speed as light objects. So it doesn't matter. This blue dot could be a tennis ball, a grand piano, or a building. They would all fall at the same speed if we ignore air resistance. So here's what we're going to do. We're going to reset this thing, and we are going to step forward piece by piece and see what happens at an acceleration of 10 meters per second squared. So what that means, that's 10 meters per second per second. Speed will increase by 10 meters per second for every 1 second that passes. So some things I want to draw your attention to on this. This area right here will show you how the thing's falling, and these areas down here are really what I want you to be interested in. T gives us the time, so that's how much time has passed, and V gives us the speed. And what I want you to see here is that when we get to time 1 second, watch the speed of this. And I'm going to play it forward to get us a little closer to 1 second, and then we'll go stepwise from there. Alright, so here we are at 0.79 seconds. This thing has been accelerating now for 79 hundredths of a second, and it's a speed of 7.9 meters per second. Now, there's information to be gathered there, but let's go to something that's mathematically easier to work with. And so I'm going to run the simulation up to 1 second. And notice the speed of the object at 1 second. At 1 second, it's traveling at a speed of 10 meters per second. Now this gives a true velocity. That negative indicates it's going in a downward direction. So that negative sign acts as the direction for this. So we can say properly that that is a velocity and not a speed. But just looking at the speed component of it, after 1 second, it's gained 10 meters per second of speed. So now I'm going to play it forward, and let's look at 2 seconds. At 2 seconds, it should have gained 10 meters per second of speed twice. So if we are correct, this should be traveling at a speed of 20 meters per second. So let's see what happens. Going to now step forward until we get to 2 seconds. and at 2 seconds, we're traveling at 20 meters per second. All right, here's the next thing to notice. This thing falls with this constant acceleration. Notice that what that does to the distance it travels in each unit of time, each period of time. So between where we first see it and where we second see it, the first and second images here, notice how small that space is, and then the space gets bigger and bigger and bigger and bigger and bigger. This makes sense because the amount of the ball, or the amount of distance the ball is going to cover in each amount or each time period for this will increase because it's moving faster and faster and faster. And so this is true of accelerated motion, that if it's speeding up, the object will cover more and more ground as it goes along. So things to remember: due to Earth's gravity, everything at the Earth's surface accelerates downward at 9.8 meters per second squared. We can round that off to 10 meters per second squared, which means that for every 1 second something falls, it gains 10 meters per second of speed.